This day is very important, yes. We feel that for mathematicians, the year 1900 was very significant. Hilbert, a famous German mathematician, listed a series of problems for mathematicians which he thought would be very influential in the following years, and laid them down as a kind of challenge for mathematicians. And we felt we should mark the year 2000. And we wanted to do that in a slightly different way, not to try and predict which direction mathematics should go in, not to influence it, but just to record the problems of the 20th century which we felt had resisted challenge most successfully, and which we would most like to see resolved. We don't know how they'll be solved or when. It may take 5 years, maybe 200 years, we don't know. But we believe that somehow by solving these problems we will open whole new vistas of mathematical discoveries and landscapes.
Well, the Clay Mathematics Institute was founded to create and to disseminate mathematical knowledge. We are, according to our statutes, we further the beauty, the power, and the universality of mathematical thinking. We do this in many ways. To create mathematics, we hire mathematicians to do mathematical research, and we hire mathematicians, some for short-term, some for long-term. We have younger mathematicians in their mid and early 20s. We call them CMI long-term prize fellows. They work for us for 3 years, 4 years, 5 years. We also have a set of programs to disseminate mathematical knowledge. That's the other half of what we do. So we have workshops, conferences, summer schools, and meetings like this meeting in Paris that we're at now. We also have people writing books for the Clay Mathematics Institute. So this is a very important part of disseminating mathematical knowledge, having the best mathematicians writing expository works to explain mathematics. Another aspect of the CMI is that we are very interested to encourage talented students to study mathematics. It's important to preserve mathematics for the future that we have a continual stream of students who are interested. Some will eventually be mathematicians, some will go into science, some will go into other things. But we must have students studying mathematics. We try to do these things in a way where they're always high level, where the people are extremely good. We try to work with leading people, people who are very brilliant. They may be quite young. Some of our prize fellows are 24, 25, 26, or they may be much older, senior mathematicians, but we try to work with the best. The CMI statutes direct us to further the beauty, power, and universality of mathematical thought. Under this theme, we gather today to celebrate in two ways.
But the other question that was asked, it was, why Paris? And of course the reason is that 100 years ago, Hilbert proposed a set of questions which would determine the direction of mathematics over the subsequent 100 years.
Let's imagine that we just have our voices initially. So we sing. We have some idea of music because we have some idea of tone. what works well together. But gradually we construct instruments. By putting those instruments together, we increase the sphere of music that we can, in fact, explore. By developing more and more instruments, by putting different instruments together, that world becomes richer and richer. It's very similar in mathematics. It's through the development of this language that we discover the abstract mathematical world, which we spend our time being fascinated about.
Well, in the school I went to in the United States, 40 kilometers outside of Boston, in Concord, Massachusetts, over the door into the classroom there was an epigram in Greek by a Greek mathematician, and I can remember it, pas arithmos eidos, which freely translated in English is, wherever there is mathematics, there is comeliness. Comeliness is not a usual English word, but it means beauty, fitting together, harmony, excellence.
One judges mathematical proofs really by their beauty. This is perhaps hard to communicate to a non-mathematician, but when you feel you've found the right proof, then everything fits together so perfectly. One has the feeling when one's writing out what really is a correct proof, that the proof gets always shorter. Whereas when you're writing out an incorrect proof, you have the feeling the proof always gets longer every time you try to fill in the details.
You find that all the ingredients that you had in your brain come together, okay? Which is an extremely privileged time. At that time, probably if you want there is a special resonance in the brain, and there is a special harmony in the brain, which makes it so that intuition becomes much, much stronger. Namely, the power of intuition is sort of multiplied by 10 in this event, okay? But somehow, you know, this lasts for some time, not for very long.
Mathematics has its own intrinsic beauty because at the same time mathematics is a science and an art. And sometimes when you have the most beautiful mathematics, which is beauty that can be appreciated by a mathematician, it turns out to have some intrinsic quality which is very long-lasting.
I was interviewed by people with a television camera yesterday afternoon, and one of the camera women asked, well, after you've solved these questions, are there any more questions in math? Will there be any more questions in math? I assured her that there would be, as long as the human spirit reaches out to investigate the universe.
There is so much still to be solved, so much unknown territory. And one of the things we are doing is to list 7 of the most famous unsolved problems of the 20th century, so that the general public will know just what we're striving for, and so that mathematicians will remember what we struggled with in the 20th century.
I will now ask Lavinia Clay to come forward to give the award to Laurent Lefort.
To give a prize is acknowledged in the public, but the real way to help is not just to run a lottery that makes a large award, but to support young mathematicians, to identify young people of talent, boys and girls, and to give them the opportunity to develop. And that's what we would like to do. We, at the Clay Mathematics Institute, have a large program for supporting young students.
Yes, there is symmetry, multiplicity, and 2 prizes.
The second recipient, it comes as a complete surprise. Alan Kahn is one of the great mathematicians of our age. We had to keep this secret. I'm extremely happy to announce the CMI award to Alan Kahn for revolutionizing the field of operator algebras, for inventing non-commutative geometry, and for discovering that these ideas appear everywhere, including the foundations of theoretical physics. Alan Kahn.
Okay, so I mean, the only thing I want to say is that, you know, for me, mathematics has always been the greatest school of humility, in the sense that every day a mathematician who does research is faced with himself in front of difficult problems and can sort of every day measure to which extent, he's unable to solve problems and he has to work hard and to keep working hard on problems. Now, what I would like to say is that, you know, one of the main purposes of the Millennium Prize is to sort of counteract one tendency which, if you want, mathematical research might be following. And that tendency would be that because young people don't have the security to work, they might tend to attack problems which can be reached easily so that they will have published papers. Now, by creating these problems, the CMI really wants to try to send a clear message, which is that, mathematics is mainly valuable because of these immensely difficult problems, which are like the Mount Everest, if you want, or the Mount Himalaya and so on in mathematics. And what we know is that if we reach the peak, first of all, it will be extremely difficult. We might even pay the price of our health or something like that. But what is true is that when we reach the peak, the view from there will be fantastic.
Mathematics is cheap and occasionally produces breakthroughs of enormous economic benefit, either directly, as in the case of public key cryptography, or indirectly, as a result of providing the necessary theoretical underpinning for science. If you were to work out what mathematical research has cost the world in the last 100 years, and then work out what the world has gained in crude economic terms, then you would discover that the world has received an extraordinary return on a very small investment. My main purpose is not so much to go into great mathematical detail about the problems, it's just to convey somehow the flavor of the problems, and then I'll say why I want to convey the flavor of them. So let's look at these sequences of numbers, 5, 11, 17, 23, 29, and then there's some other ones. If you look at it, you'll notice that the jump from 5 to 11 is 6, and it jumps up by another 6 to 17, by another 6 to 23, and so on. So this sort of sequence where you jump by a regular amount is called an arithmetic progression. Here's another one, 7, 19, 31, 43. The jump is 12. And here the jump is 30, 11, 41, 71, 101, 131. And similarly for the bottom one. Now you might ask why I didn't continue those sequences further. Well, the reason was that all these numbers in black here have in common that they are prime numbers, something of great interest to mathematicians. And had I tried to continue from 29, say I'd have gone to 35, and that's not a prime number because it's 5 times 7. And over here also are the explanations for why the next number is not a prime number. Now, once I show you that, there are some very obvious questions you could ask. The most obvious one is the second one, actually. Is there any limit to the possible size of an arithmetic progression consisting solely of prime numbers? Nobody knows the answer. I think the record that anyone's found is about 22 or 23, but that's just discovered by a computer search and doesn't really get you any closer to a solution of the problem. But let me just describe what one or two of these links are like. If you're looking at arithmetic progressions of primes, it's very natural, and Erdős and Turan did this, to generalize the question to arithmetic progressions in more general sorts of sets. As an aside, that led to important advances in ergodic theory, which is a totally different branch of maths and surprised everybody. I was thinking about a different approach to Semerades' theorem and came up with a lemma, which was a sort of an improvement of the Balog-Semerades theorem, which I talked about a little earlier. Jean Bourgain noticed that he could use that lemma to improve the best known answer so far for the Kakeya problem, the one about sliding cones about. Bourgain had earlier proved that the Kakeya problem had intimate connections with the distribution of the zeros of the Riemann zeta function, intimately itself connected with the distribution of prime numbers, as Riemann showed us, which gets you full circle back to arithmetic progressions in primes. Now, I'm not going to claim that thinking about arithmetic progressions of primes directly helps physics or something like that, but nevertheless, there's this huge interconnected web of knowledge, and you just can't afford to break bits off it. That would be my main message. My home country, England, was famously described by Napoleon as une nation de boutiquiers, a nation of shopkeepers. In England, the word intellectual is sometimes regarded as virtually a synonym for pretentious, whereas in France, intellectuals are widely admired and abstract thought greatly appreciated, or at least so one reads. The cultural case, in brief, is that knowledge is worth pursuing for its own sake. Just as one of the rewards for individual mathematical or other cultural success is a form of immortality, so entire societies, ancient Greece being the most obvious example, are remembered for their contributions to knowledge long after their political and economic influence has faded.
Wir dürfen nicht denen glauben, die heute mit philosophischer Miene und überlegenem Tone den Kulturuntergang prophezeien und sich in den Ignorabimus gefallen. Für uns gibt es kein Ignorabimus und meiner Meinung nach auch für die Naturwissenschaft überhaupt nicht. Statt des törichten Ignorabimus heiße im Gegenteil unsere Losung: Wir müssen wissen, wir werden wissen.
Okay.
Some of the problems are hard to appreciate without some technical training, but some of them actually are very fundamental problems that one can, in a way, describe a little bit non-mathematically. For example, the Riemann hypothesis, which is perhaps the most famous among mathematicians, really tries to describe how prime numbers behave. If you just pick a random number, is it likely to be prime? What is the probability that a random number is a prime number? And that actually was answered by Riemann. But if you ask, well, how in a certain range, how many numbers do you expect to be prime, and how much variation is there? Any more detailed questions cannot be answered yet, and this Riemann hypothesis somehow gives us a very deep understanding of the behavior of primes. They're very regular. It's couched in very beautiful mathematical terms, but the general idea is certainly one that can be communicated.
And the first Clay Prize problem, Millennium Prize problem, is the famous Riemann hypothesis to prove that if rho is a complex number such that zeta of rho is 0, and it's not one of the trivial, so-called trivial zeros, and minus an even integer, then the real part of rho is equal to 1/2. In other words, drawing the complex numbers here with 0 here, 1 here, and I there, they're the trivial zeros here, 2 minus 2 minus 4 minus 6. All other zeros should lie on this line, real part equal 1/2. Well, that was 140 years ago. Whoever solves that problem will have earned his prize. Some of the many of the very greatest mathematical minds in between have thought about that problem and have failed to solve it. On the other hand, there's every reason to believe it's true.
So it's a mathematician, and he worked for 30 years on this problem. And after 30 years, he's sort of tired and so on. So he's ready to do anything to try to see if he can get the answer. So it turns out that he has some acquaintance with the devil. And finally, he decides to sign the papers that he sells his soul to the devil. Okay? And then immediately, of course, he asks the devil, is this Riemann hypothesis true? And the devil looks at him and I don't know the Riemann hypothesis. What is it? Okay, so the guy begins, explain, you take this function zeta of s, which is the sum of 1 over n to the s, and so on. And you analytically continue it, and you ask, where are the zeros? The devil says, I didn't know this problem. I will have to think about it. Give me 3 days. 1:30, no devil. 2 o'clock, no devil. He still waits, of course, because he already solved his soul. And at 2:15, the devil arrives, all disheveled, sweating and so on. And he arrives and he says, he's really in a bad state, I couldn't do it, but I could prove this very nice little formula. So that's the story,
Well, I'm very pleased to be here on this big occasion of the Clay Institute meeting and to help to launch the problems for the next century. I'm very pleased to see so many young people here in the audience. Of course, I'm very pleased to see old friends as well, but I'm particularly pleased to see young people because this occasion, which is really the handover from the last century to the new century. We are here to really summarize the state of mathematics at the end of one century and to describe the problems for the young people to work on in the new century. So this is really a message to the young people. This is your problems. You are the ones to whom we look for solutions of these problems. This is what's called the Navier-Stokes equations. Navier-Stokes equations. Now, the Navier-Stokes equations are the partial differential equations that describe the flow of a fluid which is incompressible but viscous. Incompressible viscous flow and the equations which describe this are very well established. They go back for 100 years, Navier and Stokes from the 19th century. They're widely used in practice. You fly on an aeroplane or you go on a boat, you thank your God that we have the Navier-Stokes equations. And they have a wide range of validity. Of course, every physical model is an approximation, but it's a pretty good approximation for most practical purposes. And it has very great practical importance, even though the mathematical theory of the Navier-Stokes equation is incomplete, it doesn't stop people using it and getting practical results. So there's a great deal of practical work going on in getting numerical results of the Navier-Stokes equations. The first equation essentially involves the partial derivative of u and the nonlinear term here involving the product of u and the derivative of u. And there is a viscosity term, a coefficient nu in front of the Laplacian of ui. There is the gradient of the pressure, and then there is an unknown given external field, which you may say could be 0, but could be, for example, given by the gravitational field if you're studying water moving on the Earth. And then there is the divergence equal to 0 of u, which is the incompressibility of the flow. These two equations are easily deduced from fundamental principles of Newtonian mechanics, describe fluid flow of incompressible but viscous flow where nu is the viscosity, is positive number. The question is, Navier-Stokes problem is to prove or disprove the existence of smooth solutions for all time under reasonable assumptions on the initial data and on the external field. Question is, given reasonable conditions, boundary conditions or initial data, prove the existence of solutions for all time. Smooth solutions remaining smooth for all time. That's the problem. Is that true? Can you prove it?
But the problem posed there is extremely difficult. If I spent 10 years on it, I might just about figure out why the problem is difficult. I don't think I'll be able to solve it. but okay, but it's really good to have these problems, you know, to have some focus points like that to, you know, as like these impossible goals. It's good to have a few impossible goals. I think it gives you a sense of long-term vision and not just focus on just very short-term things, like not just things that you can do immediately, but yeah.
I'd like to invite you to a champagne and some hors d'oeuvres outside, and also to say if this evening you solve one of the problems, send it to a journal. Don't send it to us, but in 2 years we'll consider it for the prize, and each prize is $1 million.
Mathematics does sometimes give the impression of being spread over such a large area that even one mathematician can't understand another. But if you think back to 18th century mathematics, most modern mathematicians would understand it all, and in a much more unified way than the 18th century mathematicians. I think this dispersion that one senses is really just because we don't understand it well enough yet. And over the next 200 years, all our current methods and proofs will be simplified, and people will see it as a whole, and it will be much easier. I mean, nowadays, most high school students will study calculus. That would have been unthinkable in the 17th century. But now it's routine, and that will happen to current mathematics in 300 years' time.
Je suis aussi très heureux pour Alain Cohn, que son travail extraordinaire ait été honoré aujourd'hui.
Fabric of arches, a saddle point like this, no matter how you orient it, it is always going to present some kind of compressive arch structure.